Well, good afternoon and welcome back to physics for today. We are going to visit the lesson that we started last time we were together, and you're going to feel that it's very similar to what we just covered with regards to linear expansion, but now we're going to look at the expansion of the whole object rather than just linearly, and that is called volume expansion. And if we look at the first example in your notes, which, by the way, if you haven't turned there yet, please hustle up and do so. We have already listed the variables on the side, which is what I will expect for all of these problems when you're doing them and when you're showing me that you know how to do them. So you might as well get in good habit now. And as we read through this question, a gasoline tank holds 60 liters. That is the original volume, assuming that the tank is full, which it says that in the second sentence. The temperature changes from being 20 degrees to 45, a hot day. And so that's an increase of 25 degrees Celsius, and I'm writing it in the incorrect place. That is your change in temperature. And we are dealing with gasoline, so we're going to look back at our chart, which is a few pages back in your notes. We're going to find gasoline on the list, and we will go over to the coefficient of volume expansion, and we see the number is 950 times 10 to the minus 6. Now, just going to grab my highlighters here. So again, it's 950 because we're talking about gasoline, and up here we see that all these values are multiplied by 10 to the minus 6. Let's put that number into our information here, 950 times 10 to the minus 6. Please put the unit there as a reminder that it is simply there to cancel out with the other degrees Celsius. So when we find our change in volume, it will be measured in liters. I will expect you to write the formula down without any numbers in it, showing me that you understand this is the formula you would use. Clearly on this assignment, it's obvious which formula to use. As the unit goes on, though, and we run into more formulae or formulas, it won't be always as clear. So I want you to show me that. And again, good habits will lead to good results later. Let's all take our calculators out now and multiply, multiply these numbers together. 60 is your original volume times the coefficient times the change in temperature. And I get an answer of 1.425. And as I said before, the degrees will cancel out, leaving you with liters. I like to put the plus sign there. It's not required, but it shows that it's going to be an increase in volume, not a decrease. It's going to expand, not contract. Very similar to what we did with linear expansion. Let's try one more. Same process. We list on the side the variables and see which ones we have and which ones we don't have, and that will tell you usually what you're looking for just by process of elimination. I see temperatures, it goes from 12 to 5, so I'm going to put minus 7 degrees Celsius, the minus as a reminder that this is going to contract. The original volume this time is in milliliters. We do not need to change it to liters. This can be in any unit of volume. And we are dealing with antifreeze. So again, I'm going to go back to the chart. I'm going to look for antifreeze, and she is right there. So this time the number is 108. Comparing that to the gasoline, because the number is less, means that antifreeze will expand or contract a less amount or a lesser amount compared to the gasoline if there's the same temperature change. And once again, we're looking for the change in volume. So again, this is more calculator practice than anything. So the original volume multiplied by the change in temperature multiplied by the coefficient. And the order of those don't matter with multiplication. So I'll write them down in one order this time and another order the next time, and I really don't care which you write it in. So let's multiply it with our calculators. 250 times minus 7 times 108 to the power of minus 6, and I get an answer of 0.189, and it's negative. And that's milliliters. What's the change in volume? It is a decrease of that amount, or a contraction maybe would be even a better word. One more example, and then I'll let you get to work. This example is a comparison of balloons, and you'll notice that the units are not in milliliters, nor are they in liters. They are now into centimeters cubed. 1 centimeter cubed, by definition, is 1 milliliter of water, assuming that the centimeters cubed is also water. So these balloons, and I don't know that you need to draw them, but it's a little bit more fun that way, have a certain amount of space that they take up. And we are supposed to, given a change of temperature of 30 Kelvin, compare their expansion. The problem is we don't have a number for balloons. We don't know what the coefficient is for balloons, so we can't just calculate the answer and come up with a number comparison. What we can do is consider what factors will affect each balloon. And there are 3 factors of volume expansion, just like there were 3 factors for linear expansion. One being the original volume. So when we compare the original volumes, clearly the 100 centimeters cubed is twice as big. There would be a coefficient for both, but the coefficient for both would be the same. That number wouldn't change. They're both balloons. And there would also be a change in temperature. We do know that value is 30 Kelvin. It is the same for both. So because the coefficient and the change in temperature are the same, the only variable amount, or the amount that could change the answer of the amount of expansion, would be the original volume. So to compare the volumes on any given temperature change, because 100 centimeters is twice the size of 50 centimeters cubed, then we can say that the 100 centimeter cubed balloon will expand twice as much because it's twice the size, or it occupies twice the amount of space. So that's all the information you need. You are going to get out your colored assignment pages, and you are going to get some practice questions. On the front of your booklet, you did some of the questions. They involved linear expansion. At the bottom of your page are the questions that involve volume expansion. There are no answers on this page. As you work, you will need to compare your answers with those around you and decide what the right answer is together. And so that would require you to first do the questions separately. If you do them together right off the bat, you'll both perhaps make the same error. Then on the back of that page is a second set of questions. Again, you have done the first few, which involved linear expansion. You are now going to do the last few, which involve volume expansion. When you are done those, you will have some time to finish your assignment that you started this morning involving the alternate forms of energy. You will need to get that done for Monday. As well, there will be a check on Monday involving volume expansion. Some things you will want to know include the factors that affect volume expansion. You'll also want to be able to do these questions and the questions in your practice assignment. And you might even want to review the definitions that we've covered so far in the heat unit. Otherwise, that's it. The expectation is that you will work diligently and quietly, even though it is Friday last class, that you will get these done, and that come Monday, that you'll be able to show that you've done an ample amount of work to be proficient at doing these questions. So that's it. Have yourself a good last class this Friday and a great weekend. I will see you on Monday.